Hello, class. Welcome back. So we see three bullet points here on the glass here. And these are some important points to remember because in terms of this class and biochemistry in general, one of our goals is to understand how organisms extract their energy. What do they do to get the energy that they need to survive? So for us as humans, what do we do how do we get our energy? Well, we eat food, right? So we get the energy from that food. And then the next thing that we need to understand is how do we store that energy? And storing energy takes energy. And then the third point here is how do we use that energy that we've extracted and how do we use that energy that we've stored to keep us alive? And so right here I say to do useful work. And so what could that useful work be? Making molecules in our cells, creating cells, having cells split. All that takes work and energy. And so our goal in biochemistry is to understand these three areas, but in terms of chemical terms. We want to understand how this all happens chemically. And we also want to do it quantitatively. We want to put a number to these processes. And so when you take a look at an organism, and let's take a look at a baby, like say a baby shark. That baby shark is going to change over time. It's going to grow. But it reaches a point where it's mature and its phenotype doesn't change. Like it's not growing anymore technically. And it's just the change of its outer, what it looks like, doesn't change very much, okay? But inside the cells of this mature shark, molecules are not stagnant. They don't just stay there. They're constantly changing, okay? So the characteristics of an organism when it's mature, the characteristics don't change over time. Or if they do change, they change very little. But inside the cells, constant change, and a lot of it. So for example, if you go back and think about your last meal that you had, and if you had any glucose, when you consume glucose, and it doesn't just stay glucose, right? It's going to change, and it's going to change rather rapidly. What could it change into? It could change into carbon dioxide. It could change into fat. It's going to change into other intermediates in the Krebs cycle. And so it's constantly being changed. Now, when we take a look at our blood glucose levels, why does the blood glucose level stay relatively constant throughout all of the day? Right? Well, it stays relatively constant because what you're doing is you're intaking glucose throughout the day, and you can also synthesize it. And so that intake of glucose and synthesizing glucose is going to equal the breakdown of that glucose. Breakdown or the conversion. So our blood glucose levels stay relatively constant throughout the day because we're consuming it and we're synthesizing it, and that the rate at which we intake glucose and make it equals the rate at which it is being broken down and getting converted into carbon dioxide or fat. And so that process right here is called a very important term. It's called dynamic steady state. Okay. So for a living organism, we are operating under a dynamic steady state. Now, I want to compare that to what we understand from equilibrium. So right out of the gate, equilibrium isn't the same thing as a dynamic steady state. Okay? So let's say from a chemical perspective, and so we're not looking at a living organism. We're just going to look at a chemical reaction. Let's say we take a molecule A plus a molecule B, and we want those to react. And so we are going to have an equilibrium process. And when those two react, I'm going to say they're going to form a bond between A and B. So here we have two separate molecules. Here they have formed a bond. Okay? And equilibrium is telling us that the net change is zero. What does that mean? A net change of zero. What that's saying is if we're going in this direction, A and B are being converted to this one molecule at the same rate as A and B, this one molecule is being broken down into two, so going in the opposite direction. Okay? So there's going to be a net change of zero because whatever is converted in this direction is going to be offset by the conversion back. So there's no change. That's equilibrium. Okay? But a living organism cannot reach equilibrium in this sense right here. If a living organism reaches equilibrium, they're dead by definition. But a living organism is operating under this dynamic steady state. And that dynamic steady state it has an equal sign right here, but it's not because the breakdown and it's not this process, this process right here isn't like this one. You see? So in a chemical term or in a chemical reaction, I'm not continually adding A and B. See, I'm not doing an intake. Do you see how that's a little different over here? In a living organism, I'm constantly putting in glucose, and that's going to be equal to the breakdown and the conversion. Okay? So just to reiterate the importance of this concept, living organisms, if they reached equilibrium in these terms right here, they're dead. But when you're alive, you're under a dynamic steady state. And we operate that way because we need to constantly be extracting energy. We are constantly needing to store some of that energy, and we're doing these two processes so that we can do useful work, so our cells can stay alive. And what are some examples of that useful work? Making proteins, making nucleic acids, breaking down glucose into other molecules. We're doing, and even work such as cell division. Okay? So let's go back to general chemistry, organic chemistry, and just review our thermodynamic parameters. Because remembering our thermodynamic parameters and the first law of thermodynamics and the second law of thermodynamics, we need to remember these things is because living organisms have to and do obey the laws of thermodynamics. Right? So in general chemistry and organic chemistry, we learn about thermodynamics in regards to reactions, not in living things. But now we're shifting over to looking at those principles in living organisms. Okay? So let's do it from a non-living perspective here. Let's say we have ourselves a beaker, okay? And I want to do this reaction A plus B. What I have here is a solvent in a beaker, and we have ourselves a bench top that beaker's on, okay? And the reaction that we want to do is taking A and B that's floating around in this solution, and we want them to react to form this one molecule. All right? So with thermodynamics, we have to identify what is our system and what is our surroundings. And when we're talking about chemistry and how molecules react, that is by definition our system. So our system right here is the molecules of interest. Okay? So that would be that whole process right there. That's our system. Everything else is the surroundings. The solvent that it's in, the beaker, the bench top, that is all the surroundings. So what we could say is everything else. So our surroundings is the molecules of interest doing the reaction, and everything else is the surroundings. And the law of thermodynamics coming into play teaches us that the energy of the system, okay, well, I'm trying to abbreviate here like this. So the system, energy of the system plus the energy of the surroundings has to equal the energy of the universe. All right. And we've learned from previous classes that the energy of the universe is constant. You cannot create nor destroy energy. It's all the energy in the universe is there. What happens, though, is energy can change forms. So whenever you have a change in the energy of the system, the opposite but the same magnitude is going to change in the surroundings. So for example, if you have a system that gives off heat, the surroundings is going to absorb that same amount of heat or the same amount of energy. It cannot be created nor destroyed. So I'm going to, let's see here. So let's clean off this board. So in biochemistry, we're going to be looking at reactions, but now the reactions are inside of a cell. So we want to, let's, for example, look at this reaction here where you take glucose, okay, and you convert that to glucose 6-phosphate. All right, that's a reaction. There's going to be energetics involved, thermodynamics, and we want to know how much energy this costs and how that energy is going to help the cell. And so we're going to use chemistry, the laws of thermodynamics, just through the lens of the reaction occurring in a living cell. And so when we take a look at this particular reaction, what is our system? Our system is the glucose getting converted to glucose 6-phosphate. What is the surroundings? The cell, the cytoplasm, everything in that cell, everything outside of that cell, everything else is the surroundings. And so it is what makes up the universe? Two things: the system plus the surroundings makes up our universe here. Now we have some definitions here, okay? We have different types of systems. We have an isolated system, okay? And by definition, an isolated system, and I'm going to read this to you so there's no mistakes in definitions here. So if the system exchanges neither matter nor energy with its surroundings, it is said to be isolated. So we could sum that up in our own words. An isolated system does not transmit or give energy to the surroundings or physical matter. All right. So a good example of this would be a thermos. Okay. Now you can take a thermos and put in cold things or hot things. And a thermos is now let me take a step back, because technically there's really not a purely isolated system, but this is as close as we can get. Well, I take that back. There could be closer ones, but for my purposes here, my example of a thermos is going to be considered an isolated system. Because when you have something cold in that thermos, okay, why does it stay cold? It's because heat from the surroundings can't get in, and no energy can from this inside the thermos can be released to the surroundings. So there's no transfer of energy. And in a thermos, you have a lid on, so no liquid can be taken out or no liquid could be added to. Okay? It's completely isolated. There's no change of matter nor energy with the surroundings. You can then have what's called a closed system. Okay? And a closed system is something that exchanges energy with the surroundings, but no matter is transferred to the surroundings. So let me just read the verbatim definition, okay? So if the system exchanges energy, but not matter with its surroundings, it is a closed system. So a good example of this would be going back to general chemistry when you were looking at calorimetry, when you were trying to find the specific heat capacities of substances and whatnot. And so you have that coffee cup calorimeter, right, where you stick your substance in there and you're measuring the change in temperature of the water. So the water is the surroundings, and the object that you added in there, or the reaction that you're doing, is going to change the temperature of the water. And so what has happened in a calorimeter? The surroundings, which is the water, increased or decreased its temperature. So in a closed system, you are exchanging energy with the surroundings. But in a calorimeter, you're not adding water, you're not adding things to it other than just that, other than your system. Okay? So it's completely closed. Now you probably guessed the third one is an open system. Okay? By definition, if the system exchanges both energy and matter with its surroundings, it is an open system. And an open system is living organisms. Okay. So an example of an open system would be a tree. We see that the tree can take carbon dioxide from the surroundings, and they can trees convert that carbon dioxide into what? Oxygen. And what does the tree do with that oxygen? It releases it back to the surroundings. So it is taking matter, carbon dioxide, from the surroundings and giving back to the surroundings oxygen. All right? And the energy transfer is happening when it's absorbing energy from the sun, and then that energy is being used to create these molecules and things like that. Okay? So a living organism is going to obtain energy from the surroundings in two ways, two very important ways. Okay? So the first way that a living organism gets its energy is chemical fuels. All right? So chemical fuels, living organisms can get that from glucose, for example, consuming glucose. All right? And then they take that glucose, all right, so let's do this. They take that glucose and they're going to oxidize it. And they're going to oxidize it and change that into different products over here. Okay? And that chemical reaction of oxidizing glucose or changing it into something else can give us energy. Okay? And then the second way that living organisms can obtain energy from the surroundings is from the sun. And a prime example of that would be photosynthesis. All right? But looking at all of this, the big thing that you need to remember is living organisms, even though they seem to do things differently than what we've learned in general chemistry and organic chemistry in terms of thermodynamics, open systems / living systems still have to obey the laws of thermodynamics. They can't break those or violate them. Okay? And the first law of thermodynamics is energy cannot be created nor destroyed. Living organisms do not violate that law. So now, let's go and talk about DNA for a minute. So I'm going to erase this board. So DNA is a very well-organized molecule. It's what's responsible for our genetic information. And DNA is composed of nucleotides. And we learned this in biology. We have A, C, T, and G. Adenosine, cytosine, thymine, and guanine. Guanosine, there you go. And those 4 nucleotides compose our genetic makeup, right? But DNA is a very well-organized and well-structured molecule. And it has to be because it contains all our genetic information. It has to be organized. But we've learned from the human experience that if you want to keep something organized, say your room or your house, it takes effort. It takes energy. And same thing with making our DNA. Because yes, DNA is just composed of these 4 nucleotides. But what are the odds if you had all these nucleotides just floating around in a solution? What are the odds of them coming together to make your individual genetic code? Like, that's just impractical, improbable. That's not going to happen. But in order for DNA molecules to be replicated, and you have to expend energy to keep it organized, right? But the second law of thermodynamics states that nature has a tendency to go from order to disorder. But what we're doing is the kind of like the exact opposite here. We need DNA to be organized in order for living cells to function. But free nucleotides is more disorder. So the second law of thermodynamics says, hey, we go from order to disorder. But if that happened in our cells, we would cease to exist. So how do we wrap our minds around this? Isn't that kind of like violating the second law of thermodynamics? And technically, it's not, because we're going to talk about Gibbs free energy. It's not when we look at a process, okay? Well, before I get to Gibbs free energy, what is that second law of thermodynamics describing? Okay? When you go from order to disorder, that's the law of the universe. Remember this term right here? Capital S. That is what? Entropy. Entropy is simply the measurement of disorder. And so if you have a system, you have a beginning state and a final state. And so we're going to take a look at the change of that entropy. So you have a reaction. Okay? So let's say if we did A plus B and we did a reaction, what has happened to the change of entropy? This is what we started with. This is what we ended with. Entropy is looking at disorder. So here I have two molecules, two separate molecules, and over here I only have one molecule. And so what has happened in this particular example? I've gone from more disorder to more order. And when you have a situation like that, when you go from disorder to order, you are going to have a negative change in entropy. But if you have a change in entropy, all right, in which you go from order to disorder, so we could just use our same example, really. If we have one molecule here and we break that up into two molecules, we see that more organized, less organized, and when we have that process occur, we have a positive entropy. Okay? So that's a measure, or the way that we describe randomness or disorder, the change in entropy. Another thermodynamic term that we look at is, you remember this one? Capital H. What does that stand for? Enthalpy. Enthalpy is simply looking at the energies of the bonds in our molecules. So when we take a look at this molecule AB, enthalpy is looking at how much energy was released when A plus B came together. When bonds are formed, energy is released, typically as heat. And so that's what enthalpy is looking at. It's just looking at all the different bonds and the energies it released when those bonds formed, and what is the energy required to break those bonds. So think of enthalpy in terms of the energy associated with when a bond forms. Okay? And then the change of enthalpy is going to look at the final state and the initial state, looking at the differences in those bonds. Now, we can put this all together in an equation that you have already seen before, and that's the Gibbs free energy. Okay? And Gibbs free energy is represented by G, not as the G in the nucleotides, but in terms of thermodynamic parameters. And Gibbs free energy equals the enthalpy minus the absolute temperature, so temperature in Kelvin, times our entropy term. That is by definition of our Gibbs free energy. Now, the change in Gibbs free energy, what does change mean? It's just looking at so in terms of a reaction, it's looking at the difference in energy between where the starting materials are and where the products are. So if we just look at a Gibbs free energy on the y-axis and a reaction coordinate on our x-axis, we're just looking at Gibbs free energy in these terms. We have our starting material right there, and let's say our products are down here. What is the energy difference between those two? And you can just extrapolate out here. You see the energy difference there between the starting material and the product? That right there is the change in Gibbs free energy. And so we have to adjust this equation here. Change of Gibbs free energy is also going to be the change of enthalpy minus temperature times the change in entropy. And what's so useful about this equation now is if we go back to when I was talking about DNA is organized and the nucleotides are less organized, and I said, hey, how can we do that when the second law of thermodynamics says nature typically goes from order to disorder? So, well, I was looking at it with a very narrow view. In order to see if this process occurs, you have to look at Gibbs free energy. And that is composed of three components. We have enthalpy, temperature, and entropy. When we look at all three of those thermodynamic parameters, then we can better understand if a process can occur or not. Now, what I mean by occur, let me correct myself there. We're looking at to see if a reaction or a process is spontaneous. And in order for a process to be spontaneous, the Gibbs free energy, the change in Gibbs free energy has to be negative. And if you have a Gibbs free energy that is positive, then it is not spontaneous. So if a reaction is spontaneous, once you get the reaction going, it will continue to proceed. So, for example, you are at a campfire and you haven't started the fire yet. You just have a pile of wood. The reaction's just not instantly going to just start by itself, right? You have to get it started by adding a match. But once the fire is started, that process is spontaneous. You don't have to continually input energy in the form of a match to keep the fire going. All right? So that's what a spontaneous reaction looks like. And so when we take a look at this little energy diagram here, we can draw the curve like so. And so that distance there between the starting material and the products, that's the Gibbs free energy. And what is the sign of that Gibbs free energy? That is going to be a negative value because the products are lower in energy than the starting material. Because whenever you calculate the change in something, you are going to look at the final minus the initial or the starting point. And if I just look at this y-axis here and just put values here, these are just random numbers, but what if I put 10 kilojoules per mole there and 5 right there? Do you see how this number is going to be negative? Because the final is our product. We're doing a reaction. That's our final product there. And so we see that's the energy level, and that's a 5. So I'm going to put it there, minus the energy of the starting materials. That's what you started with, or the initial energy. And that is 5 minus 10 equals negative 5. So that gives us a Gibbs free energy change of negative 5 in this particular example. But the main point to get from this is it's negative. So that makes it spontaneous. So when you have a process that looks like this, and your y-axis here is Gibbs free energy, then this process right here is called a exergonic. That is an exergonic process. Now, some of you are going to be like, hey, I thought it was exothermic. All right. Well, an exothermic process is when you are looking at a reaction in terms of enthalpy. So if you had a reaction that had starting materials and you were tracking and measuring the enthalpy to go to products, that process right there would in fact be an exothermic process. All right. So you just have to double check your y-axis to understand if it's exothermic or exergonic. All right. So if you have a process that looks like this, or something like that, what would we call that? That would be, so there's our starting material, there's our products, and so that is endothermic. And I got that got caught off a little bit there. So endothermic. But if your y-axis was Gibbs free energy, okay, so let's change it to Gibbs free energy right there. What would the name be there? That would be endergonic. And when and you spell that like this, endergonic. And my C was cut off. All right. So let's clear off this board. So if we come back to DNA as our example, DNA is composed of all these nucleotides, right? So there's our nucleotides. So there's more disorder here. But we want to take these nucleotides and turn it into DNA, which is basically just taking these and forming these covalent bonds like that. And so there's there's more order over here. Okay. So based off of looking at it through the lens of entropy, that would be a change of entropy that's negative, right? Because we're going from disorder to order. Okay. Well, then when we take and look at all the enthalpies here for these bonds that are getting formed, and we consider the whole Gibbs free energy here of this process of going from nucleotides to DNA, our Gibbs free energy is still positive, which means it's a non-spontaneous process and it's not favorable. So you have to think long and hard here. How are we still alive then? Okay. How can that even work then? Because the laws of thermodynamics says making DNA is not going to work. But it's still not breaking the laws of thermodynamics because of this concept right here that we can couple reactions. Okay? If we can couple reactions, and after coupling these reactions and we get a negative delta G, then it's a spontaneous process and it's going to work. And so what I want to show you is an example to kind of help illustrate this concept in terms of a mechanical model. And so I'm going to use a mechanical model to explain coupling of reactions. And then after I use that mechanical model, I will then show you it in chemical terms. So we can relate it back to, okay, how do nucleotides form DNA when the Gibbs free energy is positive? Well, it has to do with this coupling idea, coupling reaction here. Okay. So let's just build ourselves a triangle here, okay, like so. And let's say I have a block, okay, on the ground. So let's give ourselves the ground there. Now what happens if I take this block, pick it up, and put it right here? Okay. We know that it's going to slide down that incline until it gets back to the ground. So from this point to this point, what has happened to the potential energy? Well, we have increased the potential energy of that object because we moved it up higher, right? And so we know it's going to go down like that. Okay. But what if we have, let's build ourselves a pulley system. Okay. What if we took this large block right here, and we'll put it right here, okay, and we're going to attach it to that pulley system by a string, and then we take and attach that string to, let's just say, a tinier block, right? Like that. Now, naturally, if we had this system right here, and we wanted to get that tiny block up the hill just by itself, is it spontaneously just going to climb up this incline? No, it's not. That's not a spontaneous process. But if I put that little block right here and let go, that is a spontaneous process, right? Because it's going to slide down that incline. But our goal here is to get this block up here. But it's not naturally going to do that. So what we can do is kind of make this pulley system here, that when we attach this bigger block to this tiny block by this rope and pulley system, when we let go of this big block, you see that it's going to go down. And what is it going to do to the small block? It's going to pull it up. So this larger block has been coupled to this smaller block to get it up the incline. And that's the same concept that we want to use in chemical terms to go for, let's say, example, our nucleotides right here. We want to get those nucleotides into what? DNA, which is at the top of this incline. And the way that we can do that is by coupling. And this, making this nucleotide go up here, is now a spontaneous process because it's coupled to this larger block. Because when I let go of this larger block, it will spontaneously go down the incline. Okay. So let's take a look at this in terms of chemical a reaction. Okay. And for this example, instead of looking at DNA, because forming DNA is a much more complicated process. So I want to look at a more simple idea here, or a more simple reaction, and that is taking glucose. Okay. I want to take glucose and I want it to react it with inorganic phosphate. So P sub I just stands for inorganic phosphate. And I want to do that because I want to make a molecule called glucose 6-phosphate. Like that. That's what I want to have happen. But when I take a look at the Gibbs free energy of that process, it looks like this. No, that's just a G. That's our reaction coordinate. It's going to look something like this. Like that. So this is our starting materials, which is glucose and inorganic phosphate. And this is our product over there, our glucose 6-phosphate. And you see, when you take a look at this, that energy difference right there, that's the Gibbs free energy, and that is going to be a what? a positive change. So that's not a spontaneous process. Okay? So we would call that an endergonic reaction, right? But what if we take a look at a different reaction? Okay? What if we took, so I'm going to erase this now. What a total and separate reaction. What if I took ATP, like that, adenosine triphosphate, and that's going to be converted into ADP, adenosine diphosphate, plus our inorganic phosphate right there. So what we're doing here is, I don't need you to worry too much about the structure of ATP right now. All you have to understand is that this molecule has 3 phosphates. And now it only has 2, these adenosine diphosphate. And so that we have 3 over here, 2 there, but this one fell off. So there's our 3rd phosphate. And that process right there, okay, if we look at the energy diagram of that, Gibbs free energy, our reaction coordinate here, we're going to have something that looks more like this. Okay? And now look at that. Gibbs free energy change right there. That's definitely going to be a negative. So that would be our ATP right there, and that's our ADP plus inorganic phosphate as our products. And that process is negative. So very, very favorable. So there's another exergonic example right there. Okay. So now we have 2 reactions. One right here, and I'm going to go Gibbs free energy 2. That's going to be a large negative value. And then this one up here was our Gibbs free energy, our first reaction, and that had a positive value. Okay. Now, if we go to our analogy of the large block being coupled to a tiny block on a pulley system, hopefully what you notice in the diagrams that I drew, this right here, the pink reaction is the large block. And the glucose reaction up top here is the small block. Okay? So if we couple those together, so the way that we could do that is let's add the reaction together. If we add those reactions together to form one reaction, we see that the inorganic phosphates are going to cancel out. And so our third equation is going to look like this. Glucose plus ATP is going to turn into ADP plus glucose 6-phosphate. And I think I'm going to run out of space here. Nope, made it. Okay. So that's our third reaction. And that's going to be labeled like that. But what is the Gibbs free energy of that third reaction there? Now we learn in general chemistry about Hess's law. So because we're adding these 2 reactions together, or coupling them together to form this one reaction, what is the energy for this whole process right here? And that's what, if we look at the energy diagram, okay, Gibbs free energy, reaction coordinate on the x-axis there, we're going to see something that looks more like this. Like that. So there's our starting materials. So that would be glucose plus ATP, turning into our product, which is ADP and glucose 6-phosphate. Look at the Gibbs free energy. When you couple those reactions together, that Gibbs free energy is going to be what? Negative. It's going to be a negative. And how do I know it's another way that I know this is going to be negative? Is because Hess's law states that we just add these two reactions to get our third reaction. So the Gibbs free energy of that third reaction is simply the Gibbs free energy of reaction 1, and the change of Gibbs free energy for reaction 2. All right? And I know that this Gibbs free energy right here is a very large negative number. And I know this Gibbs free energy of reaction 1 is a positive number, but that Gibbs free energy for this top reaction was a small positive value. So we have a large one right here, a large negative, and a small positive. And when you add those two together, what are you going to get? At the end of the day, you are going to end up with a negative Gibbs free energy. And so going from glucose all the way to glucose 6-phosphate by itself is not a spontaneous process. But when it's coupled to ATP and this second reaction, it does work. And so that same principle that I've taught you here applies to DNA. If you want to make DNA, you're going to couple it to other reactions that are favorable. And then the overall process will also be spontaneous.